Hello, this is Deliverable 2 for Emily and Jason for Dr. Fahrman's class, Engineering 2130 for the fall of 2024, and I apologize if my voice sounds a little rough. I've been pretty sick these past couple of days. Okay, so in this video, we are introducing pulley systems. So from statics, you'll want to either review your notes or just refresh your memory on tension and its characteristics, especially among one rope, if there's tension on one side of the rope. Is it continuous on the other side? So you'll have to refresh your memory on that. Then you'll also have to remember how to draw free body diagrams, especially in terms of which forces go which ways. This will help you with the summation of forces and other things you'll have to do in the pulley system problems. Then you'll also have to refresh your memory on the equation of force equals mass times acceleration. Then just a side note for this problem that we'll be going over in the video today and for any future problems, whenever you do summation of forces, you must draw a free body diagram, because that helps you keep track of where your forces came from, the directions they came from, so if they would be negative or positive or not. So you have to draw a free body diagram whenever you do summation of forces, which you'll see in the problem we go over today. Then just a little refresher on imperial unit system. The gravity measurement in the imperial unit system is 32.2 feet per second per second. The force is pounds force and the mass is pounds. And then slugs is also a imperial unit system unit, and it is pounds force feet per second per second. So this is all the stuff that you'll have to either remember from statics or just keep in mind for the problem we'll be going over in this video. Okay, so this is the problem that we'll be going over, and the given is a person is using the workout machine depicted in the figure with a weight of 30 pounds at I, and the person pulls on the rope exerting a constant force at 15.6 pounds at A. So this is A, this is I, and it asks us to draw the free body diagrams of the pulleys, so this will help us just refresh our memory from statics and also look at the new pulley systems on how we're going to do free body diagrams for each pulley. So we should have 7 different free body diagrams, because it wants us to draw the free body diagrams of all the pulleys. And then it also wants us to calculate the velocity of the weights at I at t equals 2 seconds after starting at rest, which is starting at 0 velocity, and then starting at 1.2 feet per second, which means that this has an initial velocity at 1.2, and it wants us to find the final velocity after 2 seconds while it's starting at 1.2 feet per second. Also, real quick, before I forget, there is only one rope in this system, and this is important, especially for the tension and for the forces, so we just need to take note that there's one rope. So now, to recap, the important information is that I is equal to 30 pounds. The 15.6 pounds is a constant force at A. The time that we're looking at, final time, is 2 seconds. And our initial starting velocities are 0 and 1.2 feet per second. And again, this is one rope throughout the entire system. So let's start going over the free body diagrams. So we're going to start with pulley A. So as you can see, pulley A, it has a tension or a force here and the tension of the rope, which is a force here, but it also has pin forces. So all the forces in total acting at A are the A going in the pin force going in the Y direction and the pin force going in the X direction. And then there is a tension force of FBA. This is labeled this way because it's from pulley B to pulley A. So it's FBA. And then this is just the force of 15.6 pounds. And this is the angle that you need to make sure you note in free body diagrams, because even if we may not need it for part B, we still need to know for free body diagrams the angle. If it is a given angle. So that's 30 degrees. So this is the free body diagram for A. Then if we move to B and C, these two I drew together because, as you can see right here, the tension. So because there's only one rope in this problem, the tension is consistent throughout. But especially between BC, because it is the exact same rope that we're talking about, I drew them right together. So again, as in pulley A, we have the tension of the rope, those are forces, and then the pin forces. So again, this is the pin force in Y, pin force in X, pin force in Y, pin force in X for B and C. And then we have, again, the tension force and the tension force here. Then, if we go to pulley start with pulley D. So pulley D is right here, and it is holding, so it is not connected to a pin which is fixed as they are at B, C, E, and A, but it does have another force acting on it other than the tension of the rope, and that would be the weight from the weights at I. So that's the weight force. So you can see this is the force of I, which is the weights, which is 30 pounds, and again, this is the tension of the rope and the tension of the rope. Now, if we move to E, which is here, again, it is pinned and there is tension and there is the tension forces, but there are no X forces in E because both the rope from DE and EF are going directly down in the Y direction. So there is no X force, so there would be no X pin force simply because there is no opposing force that the pin needs to oppose in the X direction. So that would be E. Then if we go to pulley F, which is down here, the same as pulley A and pulley B, just flipped, is the pin forces in the X and the Y direction, and then the tension of the rope. And then the exact same thing for pulley G, which is pulley G, the tension in the rope, and then the pin forces. And again, force FG and force FG would be the same here as they would be here. Now we are going to solve for part B. So we need to figure out the forces and the tension in order to do that. This is because of tension, because there is only one rope, as I mentioned before. There's only one rope in the system. There's only one rope in the system. Forces CD, ED, and A, which this is A, and this is CD, and this is ED. These are all equal because the tension remains the same here from this force to A, from A to B, from B to C, from C to D, and from D to E. Now this is important because it's going to remain the same throughout, so we want to focus on pulley D. That is why we have drawn the free body diagram of pulley D right here. And knowing this, if these are all equal, then that means that since FA is equal to 15.6 pounds, that means that FCD and FED are both equal to 15.6 pounds. So, given that, we're just going to do a quick summation of forces of X. Since there are no X's, it's equal to 0, and the sum of forces in the Y direction. Oh, I apologize. There is a mistake on here. So, this is supposed to be FCD plus FED plus, since it's a summation of forces, but since FI is in the opposite direction, it would be negative, so it would be FY. This would give us 15.6 plus 15.6 minus 30, which is the given weight of the weights in the problem at I, which is right here. This is equal to 30. And since these are subtracted from this, we get Fy is equal to 1.2. Now, given that, we're going to keep that, know that that's important, take note of that, know that's important, and now we're going to focus on the force is equal to mass times acceleration. Well, we have to figure out the mass of the weights, which is 30 pounds times 32.2 feet per second. Again, this is the unit of gravity in the system of units that we're using, so that would mean that the mass at I is 0.9316770186 slugs, and that's the unit that I said would come back that you need to keep in mind. So, after we figure this out, now we need to know, in order to find the velocity, which is what we're looking for the velocity, we need to actually figure out the acceleration, which we can do, again, through this equation. If we just divide both sides by mass, we're given force over mass is equal to acceleration. Acceleration is equal to 1.2, which is the force, divided by the mass, which we solve for here. So this is the equation, and this is what we get, which is acceleration is equal to 1.288 feet per second. And now, if we're going to solve for B part A, which is starting at rest, which means that the velocity, the initial velocity is equal to 0, then that would mean that we're going to use this equation, which is 1.28 times 2 seconds, because it's multiplied by seconds. So this is the velocity, so this is the acceleration, so how long it's accelerating is 2 seconds. So we're going to multiply that, which gives us this number. However, since it's at rest, we don't have to add anything because we can just solve for the final velocity since it's 0. Now, this is going to make more sense when we go over the second part, which is we're going to add this because the acceleration remains the same because nothing else in the problem changes except for the initial velocity. So we're just going to take the final velocity we saw from the previous problem and add it to the initial velocity because our process would still be the same because it's the same exact acceleration for the same exact time duration. It's just the initial velocity is different, so you'd end up adding them, which is seen here, which gives us this value. So that is how you solve for this problem. Okay, now that we've solved that problem, I just want to go over a few things that you'll have to keep in mind and look forward to for the ropes and pulley systems. So in future problems, you'll have to figure out, the rope lengths by drawing a datum, and a datum is something that if you haven't already taken or if you're taking now, you're going to learn in fluids, which is Engineering 3160. But I'll show an example of this in just a second. If we were to draw the datum on the problem that we just did, okay, so if we were to draw a datum on the problem that we just did, it would either be probably at BC, because this is a fixed point, or at GF, because these are both fixed points and you can figure out the rope lengths from there. I'll show you an example of why a datum is important and how it helps you solve the lengths in just a second. Then you also get to look forward to different numbers of ropes, because the problem that we just did only had one rope, but you can also solve with multiple ropes and multiple tensions, and then you also get to look forward to motors. Yay! Okay, so this is an example of a problem that you will learn how to solve, and it has multiple ropes. So I'm going to highlight the first rope that is in blue. So it goes around A, over C, over D, and all the way to F. So that is the first rope. So that's rope 1. So now I'm going to highlight rope 2. So this is rope 2, and it's involved in this force right here. So this is rope 2. So you're just going to have to look forward to it. Again, this is fixed here, here, and here, and it's fixed here. There is a weight, and so in this problem you're supposed to determine the speed of the cylinder given the speed of 5 meters per second. So you're given the speed here, and you're supposed to determine the speed here. So you'll have to solve for that in the future. And to give you an example of why this is important, and why drawing a datum, like if your datum was here, why this would be important. So this is an example of a problem where the datum, we've already drawn the datum, and this is us solving for the lengths. Now the reason the lengths are important is because you'll add all the lengths together and then find a time derivative which will help you solve for the velocity, which we saw in the previous problem, which you've wanted to solve for in the problem I just showed you. So again, this is not what you have to know right now, but you will learn it in the future. And then show you an example of the motors that I said you get to look forward to is this problem, where you have a motor here, and again, you've drawn the datum, and you've indicated the different ropes in different colors. So there's one in pink and there's one in blue, and you can see here that I notated all of my calculations regarding the rope in blue. So this is all the important stuff, and then this is in pink, and this is in pink. And again, whenever you have summation of forces, you must draw a free body diagram, as you can see from here and here. So again, this is not something you have to know for the problem that we solved in this video, but this is something that I just wanted to give you a heads up that you will have something to look forward to.